Hi, my name is Jason Harlow. Welcome to my V office hour. I'm going to go over my solution for Physics 132 H1F, Fall 2009 Test 2, the Freeform Part A. So this is based on Knight Chapter 33, the magnetic field, and in particular Section 33.6 on Ampere's law and solenoids. So first, let's carefully read the question. Okay, part A, a solenoid has a length L, a diameter D, and N turns, each carrying a current I. There's a diagram that shows I coming up sort of on the top, closer to the reader, then it goes down into the page, and then up out of the page, etc., until on this end it goes down into the page and emerges lower with the same current. And question A.1, with 1 point, is assuming that I is a positive number, so the current's going in here and out there. What is the direction of the magnetic field at the center of the solenoid? Circle the best choice from the following 6 possibilities: left, right, up, down, into page, or out of page. So part A2, which is worth 5 points, is if L is much greater than D, then far from the ends of the solenoid, the magnetic field is axial, which means it is parallel to the axis of the solenoid. Assume that L is much greater than D, and use Ampere's law to find the magnitude of the magnetic field at the center of the solenoid in terms of L, D, N, I, and universal constants. And then please add to the picture above a sketch of the integration path you are using in your line integral. Okay, so this is an Ampere's law question. Ampere's law states that the line integral of the magnetic field in a loop is equal to mu naught times the current through that loop. Now, line integrals may not be your favorite thing ever, but it's not too bad. Basically, you have to know what a vector field is. So a vector field is where there's a vector assigned to any point. So any point in space, there's some vector like the magnetic field which points in a certain direction. And the line integral just means that you go along that line and you find the direction you're going in, tangent to the line, and see if it's parallel to the vector field or perpendicular. If it's parallel, then you're adding, so you're integrating and getting a more positive number. If it's perpendicular, then there's 0 contribution to the integral. And if the vector is going backwards, you get a negative as you go along the integral, the line integral. So there's going to be 2 ways of answering part 1 to this question. There's a simple way just using right-hand rule, the first right-hand rule, and then we can use Ampere's law. And we eventually have to use Ampere's law in order to solve the 5-point part. So let's look at my solutions. Okay, so looking at my solutions, if you just want to know what's the direction of the magnetic field in here, one way of thinking about it is that here comes the current at the top of this solenoid, and at this point of the diagram, it's going down into the page. And so if you use the first right-hand rule for fields, you will see that the current is going down, and so if the current is going down, your thumb is going down, okay, and you bend your fingers, then just below that, it's hard to do in this video, thumb going down, bend your fingers, it'll be just below those wires, the magnetic field will be going towards the left. Okay, and similarly, on the bottom here, thumb pointing up, you curl your fingers, the magnetic field due to that, just above that, will be going towards the left. So that's one way of determining that the magnetic field in the solenoid is to the left. Another way is to set up a loop, okay, an integration path for Ampere's law. And we have here that the path has a magnetic field inside the solenoid. It's going parallel or anti-parallel to a magnetic field, and then it goes perpendicular to a magnetic field on these parts of the path, and way out here you have zero magnetic field because you're far from the solenoid. And if you use the right-hand rule along the path, so your thumb's in the direction of the path and you bend your fingers, that's the direction of positive current. And so for a clockwise path, you have positive current in going through the integration path. So from Ampere's law, this must be, these both sides are positive, and so again you have to have the magnetic field going towards the left within the loop. So going through Ampere's law now, going around this loop, we have 0 in this path because the magnetic field, if there's any, is going to be perpendicular to this path. So a dot product is 0. Same with this path. And out here we're assuming the magnetic field is very weak. So the only part that contributes is just the bottom leg. You've got B down here times L, the distance from right to left, equals mu naught times the total current going through that loop. So that's going to be the number of turns here times I, current. The number of loops that are in this rectangle is going to be little l times this number density. So the number density is the total length of the solenoid divided by the number of turns, so that's n divided by capital L. So we can plug that into here, I times little l over times n over L. The little l's cancel on both sides of the equation, and you get the magnetic field, which is towards the left, as mu naught times n times I divided by L.
Which, in fact, is exactly equation 33.16 from page 1017 of the strength of a uniform magnetic field inside a solenoid. So, that may have already been on your aid sheet, but the point is you should be able to derive that equation the same way they do in section 33.6 of Knight using the line integral. So it's just about setting up the right line to do your line integral, and so that most of the contributions are 0, and you have a very simple contribution from the portion of the line that's within the solenoid, and deriving this this magnetic field, solving for it. So, my name is Jason Harlow, and I approve this message.